Thank you, Professor Haig, and welcome you all to my presentation about the bond behavior rib steel bars with short bond lengths. Today I want to focus on the existing bond models and bond stress distribution. Something doesn't work right now. Give me a second. No, okay, sorry. In general, we need to be aware that the bond behavior influences many properties of reinforced concrete. Of course, the anchorage, reinforcement, but also crack width and crack spacing, and therefore the stiffness and load deformation behavior of RC elements are influenced by the bond behavior. From the schematic strain curves, we can already suppose that the bond force is not transmitted evenly along the transmission length. Well, when it comes to test the bond behavior, it is known that more than 30 parameters influence the experimental results. Beside material and load-related parameters, the test setup and the type of specimens play a crucial role. The most used test setup, what you can see here, is the pull-out test by Ryland. Just is relatively easy to carry out and also good to investigate the influence of certain material parameters. But big concrete cover and the internal stress flow do not match to the real boundary conditions. Other setups like the beam-ends test reflect the real conditions in a better way. It's also possible to adjust the concrete cover and the transverse reinforcement. Commonly, the bond behavior is described by the bond stress to slip relationship, where the bond stress is the result of force divided by the circumferential surface. Depending on the level of confinement, the failure can either occur by splitting and or by bar pullout, and in case of transverse reinforcement, is also a combination of those failures is possible. If we look now at the bond stress distribution within the bond zone, it is known that the maximum bond length stress depends on the bond length. This could already be observed in the early 20th century for long bond length. Therefore, the force transmission occurs not evenly, as the scheme from Marc shows here. By increasing the load, there is a redistribution of the load transfer. So the question is, what is the local failure criterion and how to describe it? So there are already various local bond models to try to tackle this issue. They are usually used to study longer bond length and also for numerical simulation, and subsequently for also for crack width determination they are used. An analytic approach to calculate the bond stress distribution and the slip for any other lengths is the bond differential equation of sliding bond, what you can see here. However, the local relationship between bond action and slip is of key importance also for this equation. Martin, for example, recommends a step size and also a reference length of 1 rib spacing, what is of course very short. Well, looking now at the bond metals, the basic idea of local bond models is to assume an average local bond stress to a local slip relationship for short bond lengths. In scientific practice, it's generally accepted that the bond length is of 5 times the body diameter or less can be declared as short. This is in accordance to the pull-out test by Ryland. This curve shows the bond model of the FIB model code 2010. Which was actually introduced by Eligahausen in the 80s. The maximum bond stress depends on the concrete compressive strength. For this model, the concrete is considered in a root term. On the right side, the results of 2 studies different for very short bond lengths are shown. They reveal that the bond stress actually increases also for bond lengths shorter than 5 times the body diameter. So we can also observe that the FIB model, bond model underestimates the bond strengths of very short bond lengths. Another approach comes from Huang, Engström, and Magnusson and respects the concrete strength in a linear way. Especially for higher strength concrete, this model matches better with the test results. Anyway, To record the local bond behavior, the tested bond length should be as short as possible. So I believe. Yeah, but there are some specifics when we need to account for when we're testing very short bond lengths. The main concern I've heard from other researchers is against this very short bond lengths is that they are susceptible for imperfections, and the results may have a bigger scatter. Yeah, therefore, this is important to be aware of these sources of imperfections and to avoid them. For very short bond lengths, it is important to pay attention, for example, for the rib arrangement. Yeah, for very okay, sorry, the rib arrangement. The results, for example, here from numerical simulations by Sobel show that there is a significant influence. How many ribs are located within the bond zone and where are they actually located in the bond zone. So there's a big scatter here because of that. Another factor is the diameter of the bond breaker, which is usually placed in front of the bond zone, depending on the ratio between the diameter of bond breaker and the diameter of steeper. A failure cone forms at the beginning of the bond length. This depth of this cone is no longer available for further load transfer. So in this case, this depth is, for example, 7 millimeters. So therefore, the question arises, well, what is actually the bond length we test in our tests? Is it really this bond length, for example, 5 times CDS, or is it actually shorter? Yeah, so to investigate this kind of questions, we did some tests and we also have some tests more planned. So the experimental program includes tests with monotonic, cyclic, and long-term loading, and 3 types of specimens, which are pull-out tests, pre-man tests, and tension tie tests. For test carried out so far, we used 3 different concretes, what you can see in this table. 1 normal strength concrete and 2 high strength concretes named C80 and C120, which are also self-compacting. The next table shows the different configuration we tested in the monotonic tests so far. Mainly, the bond length was varied between 1 and 4 times the bar diameter. So another test, we also check the influence of the concrete cover and orientation of the bar and the ribs. But today I want to focus on the results with the bond length. Fall test, we used reinforcement bars with a diameter of 60 millimeters. These drawings show a configuration of the beam-end specimen. We used the pull-out test is located at the pull-out bar. Sorry, is located on one side of the specimen with cover of 2 DS. There are 4 stirrups, 2 located within the bond zone. The right drawing shows the rib arrangement within the bond zone. For all tests, the bond length starts with the bottom of an inclining rib, so this kept the same all the time. Only for a few tests we shifted this, but we don't handle this today. The specimen were casted upside down, what you can see here, and to ensure good bond conditions. Yeah, so finally we got this kind of specimen. And then we tested this in this kind of setup. And this is what you can see in this drawing. The slip on both ends of their and the formation of cracks on the top of the surface are recorded by displacement transducers. The force was applied was pass controlled, and also recorded by a load. The load was recorded by a load cell. Beside these classical instrumentation, we already use also in the distributed fiber optic sensors in some tests. Yeah, what you can see here. Yeah, to do so, we apply the polyimide-coated sensor fibers directly on the reinforcing bar or in prefabricated grooves. And it's also possible to apply a sensor in the surrounding concrete by means of a supporting frames, or and this is shown in the right picture, for example. Yeah, coming now to the results. This diagram shows the bond strengths in regards to the concrete compressive strengths. All specimens were prepared with a bond length of 2 times the body diameter. Yeah, first of all test results exceed the approach from the model code 2010, what is here marked as a solid line. But there's a good agreement actually with the linear approach from Wang and others. Furthermore, it's noticeable that the maximum bond stress gained from beam tests are generally lower due to the reduced concrete cover. If we take now a closer look to the bond stress to slip curves for 2 different concretes, so normal strength and the high strength concrete, we can observe the following. Firstly, the normal strength concrete, both models, the FIP model and model from Wang and others, underestimate the bond strengths and the stiffness for this case. The behavior in the tests show a stiffer course than predicted by both models. For high strength concrete, there is actually a good agreement with the approach from Wang and others. So also regarding the stiffness. Let's have a look at the results of the tests with different bond lengths, and please, if we ignore the bond lengths of 60 millimeters for a moment, we recognize actually a decrease of bond strength when doubling the bond lengths from 32 to 64 millimeters. This effect is more significant for beam end tests. If we now include the breakout code, what I told you before, in our evaluation, we may consider an effective bond length. So the bond length is shortened by the depth of this breakout cone. What is, in this case, for this configuration, about 7 millimeters. So if we take this effective bond length into account, we get much higher bond strengths for very short bond lengths. Well, I know that's still it's an idea, and still we need to do some further investigation to check this kind of approach, if it's true, to get local bond stresses with very short bond lengths. Yeah, and also an option to detect and quantify those effects, differences and changes in load transfer is distributed fiber optic sensing. Yes, as mentioned earlier, we used polyimide coated fibers on rebars in a few bond tests, and we redirect one sensor several times outside the bond zone. So it comes, for example, from here, is redirected, goes from the other side, redirected, yeah, several times, so that the sensor passes through this same bond zone 2 to 4 times. The gauge spacing was set to 0.65 millimeters. Applied at the pull-out bar, we received strain curves for different load levels. I like to mention that we recognized differences in the strain readings depending on which side of the bar the sensor was applied. It might become from eccentric loading or so pre-deformation of the bar. But by comparing the strain curves, it is recognizable that the shape of the changes from a slightly concave curves to a convex curves for higher load levels. That is an indicator for a change of load transfer for higher load levels. Yeah, through local derivation of the strain curves, it is possible to get a bond stress distribution along the bond lengths. At the beginning, the load is transferred almost equally along the bond lengths, what is shown here. And yeah, it was close to the failure. The load is mainly transmitted by the last concrete creep. Yeah, there's a big local peak here. So you can also recognize different local peaks in front of ribs. So that's our options with distributed fiber optic, what we now have here. Okay, come now to a summary. Yeah, so I told you existing models maybe not adequately reflect local bond behavior. but also very short bond lengths, tests with very short bond lengths are sensitive to imperfections. They may have a bigger scatter, but we can also lower the scatter by knowing the sources of imperfections, maybe use a defined arrangement. And the bond stress distribution cannot be assumed as uniform, also not for short bond lengths. So we need to have a deeper look into that. And yeah, we can do this with fiber optic sensing. And so we will do further tests with normal strength concrete. And yeah, we already did tests with cyclic loading, what I not mentioned today, but we will do a lot of tests with long-term loading up to 3,000 hours. And we want to test longer bond lengths, see how is the redistribution of stresses there. And also we also want to do tension tie tests and want to do a crack monitoring there. And yeah, how can we apply local bond stresses come from tests with short bond lengths to such longer bond lengths? How can we match this results together? Okay, thank you for your for the funding from the German Federal Administration, and also for your for your attention. And I'm now happy to hear your questions if you have. So.
Okay, so thank you, Marc, for your very clear presentation. So it's very interesting. So now I will ask the Michel to start with the questions. So Michel, if you have some. Start.
Well, maybe what I'd like to ask you is, from your experience with this testing, how do you appreciate the way we presently calculate the anchorage lengths and with our present, let's say, codes? Yeah.
Yeah, to be honest, I'm not really happy with that. Yeah,
not totally surprised.
From what I know from the German codes, the bond lengths are actually very long.
Yeah.
Compared to my test results. When I see that, this is the first thing what I noticed some years ago already. And especially for high strength concrete, I think there is still things what we can do better. For example, just to short thing is, I tested, for example, with 3 times CDS, what is like 5 centimeters for 60 millimeter bars, and I already yielded the bar. So I had 120 kilonewtons there. So, but from when it comes to the code, you need something like, I don't know, I cannot show you. Yeah. So I think there is some cushion what we can, there's more to do there.
I think there is obviously room for improvement, and but maybe once you will have performed what you present as your outlook, it will be possible probably to reconsider some of our codes requirements.
Yeah, that's actually my goal, kind of. Yes.
Yeah. Okay. Well, thank you very much. Thank you.
Thank you. Okay, so Nicola, please, do you have questions? Yeah.
Yes. Thank you for the presentation, and really very detailed. We could see that you are really in the topic very, very thoroughly. So it was a pleasure to listen to you. 2 short questions. This last image actually that you showed kind of got me thinking about this test on, let's say, closely spaced bars. Would it be possible, and seeing like the interaction or this effect in testing, let's say, multiple bars? Because in a beam we would have, let's say, several bars in the tensile zone, and how they would interact with the bond of each other. So in seeing here that the cracks are quite extending, so with another bar on 4 centimeters to the side of this one, is that something maybe that you thought about?
So you think you're talking about splice action, yeah? Or
no, just yeah, I mean both bars in their anchorage, but closely spaced bar. And
No, this is something what I try to avoid in my test setups. I don't want to have interaction with other bars. I just want to check for one bar.
But yeah, this is my question. So do you think there would be some kind of significant interaction in any way or not? Or that this is completely, let's say, extrapolatable to any arrangement, to configuration of reinforcement?
Yeah, there might be some influence, of course, but in changes. But I cannot really. I'm not really focused on that. Sorry.
And would it be interesting for you sometime maybe in the future doing similar tests on, let's say, FRP reinforcement, which would be then basically smooth and coated bars or kind of different behavior?
Yeah. So, as you may know, that Professor Kurbach, the head of our department, is very eager to push carbon concrete to a higher level. And we also have a lot of research going on in this field, and also have carbon bars and FRP bars here, but this is not what I'm dealing with. I know some colleagues who are doing that.
Do you think you could extend the test also to this type of reinforcement?
Not me. I'm staying with green.
No. I mean, but in general, that you would recommend the test also to be tried for FRP.
Of course, we also need bond models for these kinds of reinforcement, and we made the ideas about local bond and what we need to account for in testing, and of course it's the same. So we can take a lot of ideas from my tests or from my considerations also for these kinds of bars. Yes.
Okay, thank you.
Okay, thank you. In fact, this was one of my questions because I know that Professor Kurbach is very deeply involved in carbon concrete and carbon reinforcement, and so this was a question about the broad tests and bond of carbon reinforcement with the concrete. So okay, but it's definitely for the future also one of the topic, and maybe not now. Now you are focusing to steel, but maybe in the future also this can be applied for another material. But I have one or two small questions. One is just you tested every time the steel diameter 20 millimeter or so?
No, 16.
16 millimeter.
16, yes.
Okay. And every time you are using the same diameter.
Same diameter and same arrangement, rib arrangement, yes.
Okay.
How I mentioned earlier, there are probably more than 30 parameters what you can change in testing influence. I need to try to say, okay, I try to test 3 or 4 different parameters, but I try to avoid test others. So yeah.
Yes, I understand this well. It's a very good approach, not to spread to very wide area, but still maybe it would be interesting to just to check if you go to, for example, another diameter, if there will be some significant difference or not.
I'm absolutely with you, and I did for some student work. Student made some tests with smaller and bigger bars, and so I have little results which I can compare.
Okay.
A few, but yeah, of course, that's
maybe it's not for you, but maybe for others that they can.
I know that there's also a big discussion going on, or is there actually an influence by the bar because when you take the bond stress formula, there's actually no the bar is going out of the calculations, but there may still be an influence or not. So not really sure.
Yeah. Okay, and the second question is this presentation is in fact in the sustainability life cycle assessment session. I don't know if it was your decision or decision of organizers, but still I would like to ask what you feel could be the main contribution to sustainability. Definitely the quality of concrete principle, the way to sustainability. But what is your
okay, let's be honest. Okay, so today I wanted to talk more about my doctoral thesis topic, but also also working on a project, and this project is more going into long-term loading, and there we're talking about crack with bond creep, in fact, and how does bond creep actually influence crack width of, for example, nuclear power stations or nuclear storage stations. So it comes more from this part of research where we have power stations in Germany, but in storage stations, and we probably have to use them for more than another 50 or 100 years, and they have to be really safe and so on. But they're actually not calculated or designed for 100 years of use. And what's going on there with the crack width, and how does bond creep play into that?
Yeah, okay, thank you. Georgie, do you have some question?
Yes, thank you. I enjoyed very much your presentation, and first of all, I would like to congratulate one of your last slides indicating high bond stresses. Can you show us, please, again, high bond stresses at the end? Yes, this is an excellent diagram. This is often discussed, and almost nobody indicates high bond stresses at the end or at the crack. So I am very happy that you measured. You said, I think that close to the ribs, there were the high bond stresses. And that is exactly right, I think. And this is important also for the modeling. So some of the models include a decrease of the bond stress close to the crack or and at the end of the investigated length. And I think your result is excellent to show that this is possible to have high bond stresses at the end of the investigated length, because I give you the argumentation as well, because it indicates that the bond stress in this case is a value typical related to close to the a rib distance, so close to the rib. So that's very, if we understand bond stress, not stress per millimeter square, but we understand the bond stress related or relative force, bond force related to a rib distance. This is a clear answer what you shown here.
Yeah.
This is not a question. I was very glad to see this.
Yeah, I'm
Yes.
actually also really happy to have this new kind of technology of distributed fiber optic sensing, because before we could only measure a slip outside of the bond zone and try to figure out what's going on in the bond zone, and it was always kind of black box. And now we have the possibility to get an insight.
Yes, this is a very valuable part of your PhD. I am absolutely sure. Can we go back to the summary slide, the last slide?
Yeah.
Here you indicate cracks, rather considerable cracks in the vicinity of the bar, steel bar, all of the width of the concrete cover. My question is, if you measured very high bond stresses, 30, 40, 50 Newton per square millimeter, are you allowed to use these high bond stresses for the calculation of the anchorage length? I would not do it actually.
Of course, because they are local peaks. Yeah, of course, yes. There is this this graphic from Mersch showed, that there is this shifting of of these peaks. Yeah, there's always this redistribution, but we can use these very local bond stresses maybe for numerical simulations for longer bond lengths to calculate anchorage lengths under various loading conditions if we have these local failure criteria.
Yes, I agree completely that you actually had at least 4 or 5 times concrete cover. In this case, this is a confined concrete anyway. So I agree with your explanation. The last very short sentence is only for comment. So you, in the introduction, you said that Model Code 2010 underestimates the bond stress. This is not underestimation, but this is it comes from the definition. So local, if you use local, it is not really a local stress according to the model code, but related to 5 times bar diameter. So this is an average value. If you measure 2 times bar diameter, even shorter, this must be higher. So this is normal.
Yeah.
Yes.
I think there's also might be some wrong interpretation in this for some researchers that they think everything keeps the same also for 3 or 4 or less.
Yeah, no,
things,
yes.
But there's still something going on there. And
yes, you are right.
Actually, this model is from the 80s, and maybe we need to step further and
you can show that the difference in case of shorter lengths or longer lengths, you can test even 10 times diameter, no problem. So there is a considerable influence for the bond stresses. Okay, thank you.
Thank you.
Okay,
Hope you see you in Stuttgart next year at the bond conference.
I hope so.
I will talk a little bit more about fiber optic sensing there.
Yes, good.
Okay.
Thank you.
Thank you.
Okay, so thank you very much. So it was very nice and very, very interesting presentation. So Marc, congratulations, and the same what I mentioned to others. So I wish you the successful finish of your PhD and continuation in your research work in the future. And there is a lot of space for the further research. So thank you very much.
Thank you.